Welcome students once again into the class of number theory, and as you all know we are doing the theory of congruences. So in this video we will solve several questions related to the theory of congruences. So let us see what is the first question. So this is the first question what I am going to solve today in this video. The question says, let P1, P2, P3 and so on, Pn denote increasing sequence of primes, show that for any n greater than or equal to 1, the sum of the reciprocals of these primes 1 upon p1 plus 1 upon p2 plus 1 upon p3 plus and so on 1 upon pn cannot be an integer. So here, whatever the number of primes you take in increasing order, the sum of reciprocals of these primes cannot be an integer. And one thing is clear, if you take only one prime, then the first one prime is 2, so take p1 is equal to 2. What about 1 upon p1 is 1 upon 2, and it is not an integer. Very much clear, it is not an integer. So now we will show that not only in this case, whatever the number of primes you will take, the sum of the reciprocals will not be an integer. Excuse me. So let me rub the statement first and then I'll move on to the proof of this question, the solution of this question. So your quantity x is 1 upon p1 plus 1 upon p2 plus 1 upon p3 plus and so on plus 1 upon pn. We have to show that x is not an integer. Denote this quantity, you can say P1, P2, P3 and so on Pn divided by Pk by Ck. Denote this quantity by Ck. Then what is your x? If you see carefully, the LCM will be here P1, P2, P3 and so on Pn. What will be the first term? This will be this quantity divided by P1. This quantity divided by Pk is Ck. So this quantity divided by P1 will be C1. Plus similarly here you will get this LCM divided by P2. So that means this thing divided by P2. So it is C2 plus and so on. At the end you will get C. If x is to be an integer, then this quantity must be divisible by the denominator. If a fraction, if a number of the form p upon q is an integer, then p must be divisible by q. So here also it is in the form of numerator and denominator, and if it is to be an integer, then numerator must be divisible by denominator. Suppose if possible x is an integer. What we have to prove that x is not an integer, and what we have supposed that x is an integer. So what will happen? We will arrive at some contradiction, and some contradiction will give us that our supposition is wrong and hence x cannot be an integer. So suppose x is an integer. X is an integer, that means this quantity must be divisible by this. So therefore this P1, P2, P3, Pn must divide C1 plus C2 plus C3 plus and so on Cn, and I can write this as this quantity minus 0. So what type of quantity you are looking at this time at the board is m divides a minus b. And if m divides a minus b, then A is congruent to B modulo M. So that means your C1 plus C2 plus C3 plus Cn is congruent to 0 modulo M. Now look at, what about C2? Your C2 will be this quantity. Your C2 will be this quantity. Replace K by 2. And what will happen? P2 will be cancelled out. All the rest of the primes will be there. So in C2 only there is P1 is absent. Sorry, P2 is absent. All rest of the prime numbers are there. So it is divisible by P1. You can easily see that P1 divides C2. What if you are taking here 3? So here you will get P3. And if it is P3, your P3 will be cancelled. That means in C3, only P3 is absent, all the rest of the prime numbers are there. So that means P1 also divides C3, P1 divides C3. Similarly, and so on, you can see P1 divides Cn. The only thing that P1 does not divide C1. Because if you put here 1, what will be C1? In C1, every prime number P1, P2, P3 will be there other than P1. P1 will not be there, and since P1 is prime, it cannot divide the product of other primes. So P1 does not divide C1, whereas P1 divides C2, P1 divides C3, P1 divides Cn. So here you can say P1 divides C2 minus 0, C3 minus 0, Cn minus 0, and adding all these up, what you are going to get, you will get here that your P1 divides C2 plus C3 plus and so on Cn minus 0. And once again, if you write this in modulo form, congruence form, so what you will get? C2 plus C3 plus and so on Cn is congruent to 0 modulo P1. And here it was modulo this quantity P1, P2 and so on Pn. Look at this equation. What is happening? Here it means that P1, P2, P3 and so on. Here it is written, in fact. No need to write it again. You are just looking at the board. This P1, P2, P3 and Pn divides C1 plus C2 plus C3 and Cn. Also your P1 divides P1, P2, P3 and so on, as P1 is one of the factors. A divides B and B divides C. A divides B and B divides C means A divides C. So P1 directly divides this quantity. So P1 divides C1 plus C2 plus and so on Cn, and you can write minus 0 also. So P1 divides this quantity minus 0. So that means this quantity is congruent to 0 modulo P1. So this quantity is congruent to 0 modulo P1 now. Earlier it was P1, P2, P3, Pn, and now I can write it as modulo P1. This quantity is congruent to 0 modulo P1. This quantity is also congruent to 0 modulo P1. Subtracting, what you will get? This quantity minus this quantity is congruent to 0 minus 0 modulo P1. But this quantity minus this quantity, C2, C3, Cn, all will be cancelled. What you will be left with? C1 is congruent to 0 modulo P1, and it means P1 divides C1 minus 0, or you can say P1 divides C1, which is a contradiction because we know that P1 does not divide C1. And here we are getting that P1 divides C1. So it is a contradiction. And why this contradiction is there? Because our supposition was wrong. And what was the supposition? We have supposed that x is an integer. That means x cannot be an integer. What was x? X was the sum of the reciprocals of the given primes. So that means sum of the reciprocals of any number of primes in increasing order, the sum of the reciprocal cannot be an integer. So this was the first question based on the theory we have covered in the previous videos. And several such type of questions will be there. We will solve maybe next 3 or 4 videos. We will be solving here the questions of this type. So the second question what I am going to take is next question. If a raised to the power n is congruent to 1 modulo m, where n is any positive integer, then GCD of a and m is 1. This is our next question, and the solution is once again very easy. What we are given with? We are given that a power n is congruent to 1 modulo m, and that means m divides a power n minus 1. If m divides a power n minus 1, that means a power n minus 1 is a multiple of m, so there must exist some integer k. So there must exist some integer k such that your a power n minus 1 is equal to mk. Rewriting the equation by taking mk to the left hand side and 1 to the right hand side, you can write this equation as a power n minus 1 into a plus minus k times m is equal to 1. This mk becomes minus mk. This a power n, I have written a power n minus 1 into a, and this minus 1 I have taken it to the right hand side. So a linear combination of a and m is coming out to be 1, where the coefficients are purely integers. And we know that if linear combination of two numbers, two natural numbers or two positive integers you can say, comes out to be equal to 1, then their GCD is 1 by Bezout's identity. So this means GCD of a and m is 1, and that was required to be proved. So this was another application of congruences, and more questions will come as we will proceed ahead. Next question what I am going to take is question, write down, if a is an odd integer, if a is an odd integer, then a square is congruent to 1 modulo 8. Till now we were doing modulo 9, modulo 10, and now it is the time when we are dealing with modulo 8. So how to solve it? Look at a is an odd integer. Since a is an odd integer, in the previous video you have seen that every odd integer can be written like 2n plus 1, can be written in this form. So a can also be written in this form. What about a square minus 1 then? So a square minus 1 means 2n plus 1 whole square, minus 1 means 4n square plus 4n plus 1, minus 1 will be cancelled out with this plus 1, and you will left with 4n times n plus 1. Now this n and this n plus 1, these two are the consecutive integers, and we know that if two integers are consecutive, then exactly one of them will be divisible by 2. So either this is divisible by 2 or this is divisible by 2. If this is divisible by 2, you can write 2k here. If it is divisible by 2, you can write 2k here. So in any case, it will become 8 times something. And a square minus 1 is 8 times something, means 8 divides a square minus 1. And 8 divided a square minus 1 can be written in congruence equation like a square is congruent to 1 modulo 8. So it was the third question of the day. We will do some 4 or 5 more questions in this video, and then I'll stop this video for the next one. So next question what I'm going to take is question. Write down the question first and then we will move on to the proof. If AB is congruent to 1 modulo m and a raised to the power n is congruent to 1 modulo m for some n belonging to the set of integers, then b raised to the power n is also congruent to 1 modulo m. AB, for the solution, move on to the solution now. AB is congruent to 1 modulo m. We know that if A is congruent to B modulo m, then every power of n, A power n is congruent to B power n. This we have covered in the previous video. So here also AB is congruent to 1 modulo m. So I am raising both sides to the power n. So this means A power n, B power n is congruent to 1 modulo m. Also, we are given that A power n, is congruent to 1 modulo m. And we also know that if A is congruent to B modulo m, then multiplying both sides by the same constant, by the same non-zero constant c, we get AC is congruent to BC modulo m is also true. So here I am multiplying both sides by B power m, multiply by B power n. So what you are going to get is A power n, B power n is congruent to B power n modulo m. Now read it as I am reading it. B power n is congruent to A and Bn, and A power n Bn is congruent to 1 by the same modulo m. A is congruent to B and B is congruent to C, means A is congruent to C. Bn is congruent to A and Bn, and A and Bn is congruent to 1 modulo m. By using transitivity, you can say B power n is congruent to 1 modulo m, and that is the required result to be proved in this case. And next question will again be based on the theory of congruences. In fact, not only these questions, but in several coming videos, 4 or 5 videos, we will be dealing with the same type of questions of congruences. Maybe a little bit different questions, different theory, different style, different tricks, but the base will be the same, that is congruences. So what the next question I am going to take here in this video is, the next question is, show that x square plus y square is equal to z square consisting of prime solution only. Prime solution only is not possible. Is not possible. That means what I want to say, if A, B and C are the values of x, y and z which satisfy this given equation, then A, B and C, all three cannot be prime. All three cannot be prime. Suppose x is equal to A, y is equal to B, z is equal to C is a solution to this congruence equation, to this equation, Pythagorean equation. Then ABC will satisfy this equation. That means A square plus B square is equal to C square. Now we want to show that all these A, B and C cannot be prime. At least one of them will be composite. First of all, note that both A and B, if I am taking prime, both A and B cannot be equal to 2. So even one of them cannot be 2. Suppose A is 2. Let your A be equal to 2. What will happen? 4 is equal to B square, 4 plus B square is equal to C square will give you C square minus B square is equal to 4. That means C minus B, C plus B is equal to 4. And since C and B cannot be same, because if they are same, it will become 0. They are definitely different. So 4 cannot be written like 2 into 2 here. Both these cannot be 2. So I am writing here 4 into 1. The bigger one of the two will be equal to 4 and the smaller one will be equal to 1. The bigger one is C plus B. So C plus B is equal to 4 and the smaller one C minus B is equal to 1. Adding these up and dividing by 2, you get C is equal to 5 by 2, which is not an integer. So that means A is equal to 2 is not possible. One thing we have ruled out, that the number A cannot be equal to 2. Similarly, B can also not be equal to 2. Once again, both A and B cannot be equal to 2. Because if A is 2 and B is also 2, then what you will get here, 4 plus 4 is equal to c square is equal to 8, which once again cannot give the integral value for the c. So both A and B can also not be equal to 2. Not even one of them cannot be 2. Both can also not be 2. And in the list of prime numbers, we know that only 2 is the prime number which is even. Rest all are odd. So that means all these three are odd. So that means A is odd. And if A is odd, you can write A is equal to 2n plus 1. B is also odd. You can write B is equal to 2m plus 1. And substitute these values of A, B, C there in A square plus B square is equal to C square. You will get 2n plus 1 square plus 2m plus 1 whole square is equal to C square. And what this will give you 4 common n square plus n plus m square plus m plus 2 is equal to C square. That means C square minus 2 is 4 times something. And if something is 4 times something, it is divisible by 4. So that means 4 divides C square minus 2. 4 divides C square minus 2 means C square is congruent to 2 modulo 4. So what you are going to get here is that C square is congruent to 2 modulo 4. C cannot be odd, because if C is odd, square of a number, odd number is odd, and odd number divided by 4 cannot give you even remainder. So that means C must be even. And if C is even, again you are having a problem, because if you put C is equal to 2p, then 2p square is congruent to 2 modulo 4 will give you 1 2 will be cancelled out, and you will get 2p square is congruent to 1 modulo 4. That means 4 divides 2p square minus 1, which is again a contradiction. Why? Because 2p square minus 1 is always an odd number, whatever the value of p is. 4 cannot divide an odd number. So again you are getting a contradiction. So whatever the case you will take for A, B, C to be prime, you are getting a contradiction. That means the solution cannot be completely prime. In the equation x square plus y square is equal to z square, we can never have all x, y and z satisfying this equation to be prime numbers. Another question for this video, note down the question and then we will move on to the solution. The question is a little bit lengthy, to note it carefully. Prove that if m is greater than n, then a raised to the power 2 raised to the power n plus 1 is a divisor of a raised to the power 2 raised to the power m minus 1. Also, if m is not equal to n, then GCD of a raised to the power 2 raised to the power m plus 1 and a raised to the power 2 power n plus 1 is 1 if a is even, and it is 2 if a is odd. This is a classical question, a very good question, which is based on congruence theory and divisibility as well. So how to solve this question? The solution is tricky but is not difficult. So we start with the solution now. One thing is to be noted that every number divides itself. So that means a raised to the power 2 raised to the power n plus 1 divides a raised to the power 2 raised to the power n plus 1. This is very much clear. A divides a. And this plus 1, I can write it as minus 1 and read it like m divides a minus b. M divides a minus b means a is congruent to b modulo m. So I am writing this in congruence form. A raised to the power 2 raised to the power n is congruent to minus 1 modulo a raised to the power 2 raised to the power n. Now, if a is congruent to b modulo m, then we know that every power of a and the same power of b, they are also congruent to each other modulo m. So here the same trick I am going to use. I am raising both sides to the power 2 raised to the power m minus n. Both sides. 2 raised to the power m minus n. So what you are going to get? Minus 1 raised to the power 2 power m minus n. M and n are not equal. M is greater than n. So definitely this quantity is even, and minus 1 raised to the power even is 1. So your this side is going to be 1 modulo a raised to the power 2 power n, and here a raised to the power 2 power n raised to the power 2 power m minus n. We know that x raised to the power a raised to the power b is x raised to the power a multiplied by b. Use the fact here, the powers will be multiplied, and in powers you will get 2 raised to the power n into 2 raised to the power m minus n, and adding the powers you will get to n will be cancelled and you will get 2 power m. So this quantity will become a raised to the power 2 power m. And come back from theory of congruences to the theory of divisibility. A is congruent to b modulo m, and now write it in the divisibility form. So a raised to the power, here I have written wrongly, it was plus 1 here also, sorry for that. So from modular form, from congruence form to the divisibility form, this a raised to the power 2 power n plus 1 divides this a raised to the power 2 raised to the power m minus 1. So first part we have proved that a raised to the power 2 power n plus 1 is a divisor of a raised to the power 2 power m minus 1. First part is being proved, and now we will move on to the second part of this question. In the second part, we are to show that the GCD, the greatest common divisor of these two numbers, is 1 if A is even and 2 if A is odd. So let the GCD be D. Let D be the GCD of, or leave it. I am giving this question as an exercise to you. Here, try yourself, try to solve this question, try to show that the GCD of these two is 1 if A is even and 2 if A is odd. If you are unable to solve it, then watch the next video which will come soon, and in the next video the first question which I will prove will be this one. But I want before that you prove it yourself at your own end, so that you will get some confidence in solving the questions of congruences and GCD and divisibility theory. Thank you till then. Thank you once again.